Hi everybody, welcome to a new week. Today's lesson is going to be very quick and very easy. It is the very first mathematical lesson that goes with waves, and you would have been totally capable of doing these calculations in grade 10 when you did your waves unit, but grade 10 teachers tend to try and stay away from all the mathematical calculations that come with physics, even in grade 10. So chances are you skip this. But you are more than capable of doing this with a grade 10 education. It's just grade 9 math skills. So very, very easy. And all it is the difference between period and frequency. A very quick and easy calculation that will get more complicated as you get into more advanced work that has to do with waves. So all we're going to do here are two definitions, one for frequency, one for period. We'll introduce the formulas, although they're very quick and easy formulas. Two fast examples and three very quick homework questions that won't take you long at all. So let's start with frequency. And our definition for frequency is actually just the common English language definition for frequency that you already know. I mean, you know what frequency means. It's a word that you've been using all your life. But let's write down a definition that sort of has a physics slant to it. So we'll write down the definition for frequency is the number of wave cycles, that occur in a given amount of time. Hopefully you can write a little bit more on the lines than I do on these videos. Amount of time. Okay, so it really just means like how frequently do the peaks or the crests of a wave cycle happen. The number of wave cycles that occur in a given amount of time. So for a formula, this isn't really a formula. It's more taking this sentence expression and just writing it out in a calculation instead of a sentence. So it's going to look like this. Our variable for frequency is a lowercase f. Don't use an uppercase f because uppercase is force and universally understood as force. So you want to use a lowercase f, and just taking that definition in words and putting it into a phrase that you can actually sort of see as a calculation. It's cycles divided by time. Very, very simple. And really that's it. But something interesting happens when you sub in values for this calculation. Cycles is a count. I mean, if you see 6 waves happen in a given amount of time, you would substitute in a value of 6. But there's no units on it. You don't call it 6 waves or 6 cycles or 6 meters. You would just put a number on top. Time, though, is a concept that we've been using already throughout this course. And you know already that the standard metric units for time are seconds. So you run into a weird problem. Because let's say I was doing a substitution into this formula, and I'll write in pencil now because I'm about to erase it. You would sub in a number on top that has no units in it whatsoever, and divide by a number on the bottom that's in seconds. Well, what are the units on the answer? If you have no units on top and seconds on the bottom, what do you put as units when you get a final answer to the question? It's a rhetorical question because really you don't know the answer to this yet. What would you write? Would you write nothing over seconds? Or would you write seconds to the -1? Well, to avoid this confusion, there is a standard metric unit that has been adopted for use when you're talking about frequency. And once again, it's a last name unit. And you've heard of it before. You just really haven't used it in school. It's called the Hertz. And again, it's a last name unit, so that should be an indication that it always starts with a capital, just like any other last name. The standard units on frequency are seconds to the -1. I mean, you could write them as seconds to the -1, and some textbooks actually do. But in standard industry, you're going to see seconds to the -1 written as a capital H and a lowercase z. And as soon as you see that, you just have to sort of remember and realize that that's a last name. It was a German physicist, and it's just become our standard. Now, the problem is we don't have a lot of technology that you can actually measure the frequency of that technology in hertz, because things are just traveling at such great speeds here in the 21st century. So you've probably heard megahertz or gigahertz. Very seldom do you hear hertz. Even radio stations like 98.5 or 103.3 or 97.7 in St. Catharines, that's 97.7 megahertz. 97.7 capital M, capital HC. But the standard metric unit that we're going to use in grade 11 is hertz. And period, just to go down a ways here, period is also just like the way you've always understood the term in the common English language. It's kind of the opposite of frequency. Very, very similar definition, but kind of flip it around a little. Period is how long it takes for one wave cycle to occur. For one wave cycle to occur. So it's a measure of time. And time, just like everywhere else in this course, the standard metric unit for time is seconds, and period will be seconds as well. The easiest formula for period is, because it kind of sounds like frequency, it actually is frequency if you sort of flip the definition around. The easiest formula to calculate period is to actually take the inverse of frequency. So you calculate frequency first, and then if you flip frequency around, or you do 1 divided by the frequency, you get period. And the symbol for period is a little bit strange. Period is a time, but this is a more specific time. Here, I'm going to write it like this. I'm going to put a little t there, just for the sake of this video. It is a time, but it's a more specific type of time. This is a time for one wave. So it's not like you start a stopwatch and watch a car drive down the road for 10 seconds. That's time. This is a specific kind of time, and it has a more specific variable. So instead of a lowercase t, it's a capital T. And the understanding is, when you see a capital T, it's time, but it's time for a wave, which is a little bit different. So there's your formula for period. Capital T equals 1 over F. And you could also, although I never see this written in textbooks, but if this is the formula for frequency, cycles divided by time, then similarly, another formula for period should be that, just flipped over. Time divided by number of cycles. Although I don't really suggest that you think too much about that formula, although it does come in handy sometimes. And you know, when I wrote this, writing down number of cycles, that might actually be something you want to add in here. Number of cycles divided by time for frequency. Okay. Maybe I'll just add in this in the bottom corner here. Units. So for frequency, your units are hertz. For period, your units are seconds. Same as always. This is really easy work. And in fact, I was going to put a bunch of homework questions, and I thought to myself, why? Why do like 6, 7, 8 questions when it's this easy? A small handful is fine. But let's go through a couple of examples. I learned when I was in high school, if you have a diagram that shows an actual physical representation of a wave in a question, it's always used somehow. Don't assume that a diagram is given just for some frivolous reason to make a graphic in the corner. If there's a diagram, especially if it shows wavelengths like peaks and troughs, crests and troughs, it's there for a reason. So this example says a transverse wave is shown on the right. If D equals 0.34 minutes, so I guess there's time shown on the bottom here. If this is sort of a snapshot of a wave that is 0.34 minutes long, solve for the frequency. Okay, so you only have one formula for frequency. Frequency equals number of cycles divided by time. And time has to be in standard metric units. Every value that you use in formulas has to be in standard metric units. And it's telling us that time is 0.34 minutes. It has to be in seconds. So you need to convert that to seconds, and certainly don't just jump the decimal over twice and say that it's 34 seconds. That's not the case. 0.34 minutes, if you multiply by 60 to make that conversion, is 20.4 seconds. For number of cycles, it doesn't tell you. So here's what I mean. If there's a diagram given, it's given for a reason. We need to know how many cycles are shown in this diagram from P to O, the distance of D as it's indicated. So count them. And remember, the easiest way to count wave cycles is to go from crest to crest or from trough to trough. Let's do trough to trough. I can see that that's going to be easier here. So if you start here, it starts at a trough. So from there to the next trough is 1, 2, 3, 4, 5, 6, and then half of another one. So there's 6.5 waves shown here across the page. And that's what we'll use here. 6.5 with no units because it's just a count. 6.5 waves in 20.4 seconds is what's shown here. That's a frequency of 0.319 hertz. And you really couldn't make common sense of that answer because there's nothing here to indicate what type of wave it is or what the device making it is. So you don't really have any context to say that 0.319 makes sense, but that's the answer to that question. The one on the back page. I like this because I posted this picture. I cut and pasted this picture onto this sheet, oh geez, about 8 years ago. I was building a computer at the time and I bought this chip. I bought a Pentium 4 chip. There's the frequency of the chip written right on the side of the box, 3.6 gigahertz. If you try to buy a chip today, it really hasn't gone much higher than 3.6 gigahertz. I think we're at 3.8. You might be able to get a 4. But the speed of computers has stalled at the home level. Governments have computers that are much, much faster, but the reason that they do is because they can keep their computers so cool. See, here's the problem. You've got 3.6 gigahertz worth of electrons flowing through your computer every second, and that produces a heck of a lot of heat. So our problem with home computers is we can't keep them cool enough. If you were to look inside your home computer or your PlayStation or your Xbox, if you have one, you'll find some fans that are blowing all the time trying to keep things cool. There might be some grease on the chips or the motherboards to try and keep them cool. But ultimately, things get very hot, and we have no real way at the home level of keeping them any cooler. And we can't go any hotter because, well, we can't go any faster. Because if we go faster, things get hotter and hotter and hotter, and parts will just burn out. So we're kind of stuck at this point. And I'm going to attach a video to the end of this lecture for you to watch if you're interested, because the future is we have to get away from electrons. We have to get away from electricity. Electricity is too hot, and our computers can't really go any faster because of this heat. So if we were to replace all the wires operating a computer and change them from electrons to flashes of light, photons, they don't produce heat. And we would be able to have computers that were much, much, much faster because they would be light-based instead of electricity-based. That is what fiber optics is. That's what quantum computing is, if you've heard the term. And that's what, at Niagara College, the physics program called photonics. Sorry, I had to think of the term there. That's what photonics is the study of using light to replace electricity. It's a long explanation, but I'm going to attach a video that explains what fiber optics is if you're interested. This question is a very simple one. It doesn't really say anything. It says, what is the period? And that's it. It doesn't give any numbers. What is the period of this chip? So what is the period of that right there? That's a frequency that's already given. So a really easy formula for period is 1 divided by frequency. But frequency has to be in standard metric units. And this time, if you look at this very closely, there's a capital G in front. So that's a metric prefix. It's like kilometers or millimeters, kilohertz, millihertz. This is giga. You have a formula sheet on the back that shows this. It shows a capital G, it shows the word giga, and it gives a multiplication factor. It's times 10 to the 9. It's 9 zeros. So this is a frequency, but we can't write down 3.60. This is 3.60 times 10 to the 9 hertz. It's massive. Oh, sorry, I was off the screen there. I wasn't looking through the viewfinder trying to write a calculation. 3.6 times 10 to the 9 hertz. It is this. It's this many wavelengths per second. 1, 2, 3, 4, 5, 6, 7, 8, 9. If I put some commas in here, which I shouldn't do because it's American, it's 3.6 billion cycles of electrons going through your computer every second. So imagine that heat production. Anyway, period is going to be how much time it takes for each one of these cycles to pass. And I really suggest plugging that into a calculator because you have to see if you remember how to do scientific notation. You'll get an answer that doesn't really make a lot of sense. It's 2.8 times 10 to the negative 10 seconds. That's how long it takes for one electron to flow through your computer. You'll get a little bit more sensible answers for these 3 homework questions, but try these 3 questions. The first 2 are really just quick calculations based on these examples, and actually even question 3 is too. There's a diagram shown, but you look at it kind of the same sort of way that we just did this question. But there's a different time conversion here because the time given is in hours. Try these questions out. Honestly, you should wrap this entire thing up in 20 to 30 minutes max. You've already spent 10 minutes watching this video, another 10 minutes of doing this work, maybe 20 at the most, and you're done for the day. We'll take these 3 questions up tomorrow, and we'll move on to speed of a wave, which is the next topic. And like all of the wave calculations we do in grade 11, it's fairly easy. The formula is easy. Like I said in the video last week, you're over the hump, and you're kind of on the downward slant now in terms of how difficult the work is. So take advantage of it and learn how to do everything so that you're ready for grade 12 or for college programs that are going to require this easy work, such as dental assistantry, veterinarian, civil engineering, obviously photonics if you went into that, and a few other programs. So that's it for today. I do this work right away while it's fresh, and we'll see you tomorrow.